purpose map as a grid or graph structure randomly place an initial set of APs on the map. Okay, set the initial temperature T to a high value. Example, T is equal to 100. This is just an example, okay? Define the cooling rate alpha. So example, alpha is equal to 0.95. Then we'll have an iteration. So repeat until termination condition is met. That could be, for example, T is very low or no improvement. What I mean by no improvement is no improvement in several iterations, for example. Okay, you can figure out what. So generate a neighbor solution N by any of these methods, by either relocating, and you can choose, you don't need to put all of them, an existing AP to a nearby position. We can adding a new AP at a random location, or we can also removing an existing AP. We can add, we can do several of them, not only one of them, okay? Then once we've done the generation, we calculate the fitness of the current solution. We can use the objective function to do that. And also the neighbor solution N. Okay. Let me just call it the current solution, the fitness of the current solution. Let me just call this one F and the neighbor solution N. You've seen that this neighbor solution. Okay. If N is greater than F, accept N. If N is less than or equal to F, accept n with, this is what the algorithm say, probability, I hope I'm getting this equation correctly, e to the power of n minus f divided by t. You check if maybe I'm missed out on this one. I don't remember the exact. You check this, whether there could be something missing in there. And then we're going to say next, decrease the temp t is equal to t multiplied by the rate alpha. Okay. You can put the name of the function, simulated annealing, whatever you want to call it. You can call something and you can return. So at the end, I don't have enough space at the end, I can return best solution. Okay. So my objective function would be, just as a note, my objective function, let me just delete that. My objective function would be, oops. So my objective function, let me just rewrite this. Objective function. This is what we're calculating the fitness here. Minimize the total number of APs. You can add a few, that's the main one. You can add a few things, subject to the constraints of maintaining a minimum signal strength across the entire campus. You can consider other objective if you want. You can make it multi-objective. You can say maximize, for example, coverage, uniformity, or minimize signal variation. The initial state would be randomly place a predefined number of APs on the map. Another technique would be you can use grid-based placement, so it becomes more discretized, also, to do the initialization. Next, you have the neighborhood. Definition. So how you define the neighborhood, like relocating, I've already listed it here, relocating an existing, so it's just the same thing. That's the neighborhood. I'm just going to put an asterisk here. Let me just rewrite this. Return best solution. The neighborhood would be the asterisk that you have on top here. Coolant scheduling. I'm just summarizing whatever I've written there. Cooling schedule. Coolant scheduling. It's going to be T is equal to T multiplied by alpha. You can use, this is what is known as, this method is known as an exponential decay. You can also use a geometric decay, which is T is equal to T divided by 1 plus alpha. This is known as a geometric decay. Okay, so briefly, just to give you an indication of, please verify the exponential. I don't remember if I've written it correctly, but please check. I'm just giving an example. There are thousands of ways of solving this problem. Okay, is that okay? Let me know if it's okay. If you want to take a picture, please go ahead. I don't know if it's clear. Yeah. Let me know if this is helpful. Can you just comment, please? Okay, let's proceed. Time is flying. When you work out these questions, it's already 30 minutes gone. Let's try another question. So the next question says, discuss the pros and the cons of simulated annealing compared to the meta-heuristic algorithms like genetic algorithm or particle swarm optimization. The pros of simulated annealing is it's a very robust algorithm. So it can using this concept of it uses a probabilistic method. That's why you see this exponential and so on and so forth that allows it to escape local optimum. So this concept of annealing, where you have the temperature, which uses a probabilistic approach, allows it to escape these local solutions and has improving its chances for global solution. Okay, it's also very flexible. It's easily customizable through various definition, neighborhood definition, compared to a genetic algorithm where you have to do crossovers and mutation, though you have some flexibility, but you can see how generation of neighborhood, I can define my own ones. Let me just change the color here so that it makes sense. So I have defined my own ones. These are the ones. You can define your own ones, provided it makes sense. That's why I say you have to experiment these algorithms. If you don't experiment, you will not understand anything. It also allows for parameter tuning. Simulated annealing is a simple algorithm where you want to play with alpha, the temperature, the initial temperature, the alpha, which is the change in temperature, if you want, or the cooling rate. You can also play with the termination condition and so on and so forth. The problem with simulated annealing is that it can be slower compared to these genetic algorithm and particle swarm optimization in general sense. In general, it's slower than these population-based algorithm. it's slower to converge to the global solution. It has a little bit of difficulty. It also is high in terms of computational cost, given that it has to do constant a lot of fitness evaluation of each neighbor. Also, one of the biggest disadvantage of simulated annealing is it is very sensitive to that cooling schedule. That is, whether you're using this method of whether you're using exponential decay or geometric decay, and that cooling rate itself can be, it's very sensitive to that. Most of people who are using simulated annealing tend to spend a lot of time in experimentation, in trying to get the right cooling rate, the right temperature. Don't know whether I should use the exponential decay, geometric decay, or use both. In some cases, you can see people using both. Why? Because it is very sensitive. A slight change will have a drastic effect on the algorithm. So that's for the simulated annealing. That's 5 marks for that. So if you compare it to others, if you look at genetic algorithm, just to if you want to know the pros and cons of genetic algorithm, for example, genetic algorithm is a population-based algorithm, so it's faster to converge to solutions because it is population-based. PSO will most likely be the same. The biggest advantage why we want to use genetic algorithm is because it's very efficient in handling very complex objective function, what we call multi-objective function. So you have an objective where you want to minimize this, maximize this one, and minimize the other one, or simply the maximization involves several objectives working together. Through the concept of crossover and mutation, genetic algorithm does a good job. It's less sensitive compared to simulated annealing. It is less sensitive to individual parameters values compared to the simulated annealing. So you can tweak those values. It's less fiddly to do that. The problem with that is parameter tuning can be very complex for genetic algorithm. Don't use it off the shelf. Most of the time it doesn't work well. You have to do a lot of parameter tuning. Another problem with genetic algorithm is something called premature convergence. It can converge too quickly to the solution. In most cases, this solution is not the global solution. So it converges too quickly to a local solution, not the best local solution. Also, coding genetic operators and selection rules can be more intricate than simulated annealing. Okay, I'm just going to give you some pros and cons of the particle swarm. Particle swarm is a very simple implementation. It requires very little parameters and operators compared to GA and SA. One of the biggest advantage, yes, it's true that it can handle multi-objective, but one of the biggest advantages is because it has dynamic adaptation. So if you are in an environment that is constantly changing, particle swarm optimization is very, very good. So for instance, you are optimizing routes for the traveling salesman problem, but in this traveling salesman problem, because of traffic variation, which is changing completely, this makes the environment, this could make the environment more dynamic. So in this particular case, ACOs and PSOs, SHA-2 PSO can work fine. It is also well suited for problems with continuous variables, like where the possibilities are endless. Okay, not discretized but continuous. One of the biggest advantage of PSO is it might get stuck in local minimum when dealing with complex landscapes. Okay, there is a chance that it's going to get stuck. Remember, most of these population-based algorithms, they have higher chances of reaching global solution, but does not fully guarantee a global solution. Okay. So the next question is, have a look here. Suppose you're using genetic algorithm to optimize the arrangement of a city for a traveling salesman problem. If you don't know these problems, this will be part of your assignment. You need to look for these type of problem, NATSAP problem, traveling salesman problem, CSP, and so on and so forth, so that you familiarize. These are core problems that have been defined in mathematics and AI, where algorithms use those problems because they are massive, they are complex, and they are comparable. So it's a good idea that you get to know them better. Okay. Suppose you're using a genetic algorithm to optimize the arrangement of a set of cities for the traveling salesman problem. Briefly describe how you would present the individuals, the chromosomes in the population, and the fitness function used to evaluate their performance. There are different ways of doing that. It's very subjective. There is no single answer to that, but I'm just gonna give you one answer. You can work it out later on, use your own thoughts to work it out later on, and we can validate the answer maybe on Monday. Okay, try to work out the questions on your own as well. For the traveling salesman, would be mostly traveling from one city to the other. So the chromosome, the individuals could be represented as city A, C, B, D, for example, whatever be the name of the city, or if you want to use abbreviations for that city. The fitness function, so you can give some example. Obviously, to answer this question, you need to give a little example that there will be combinations of cities. You have to explain that, and then you show how the chromosome to get the 2 marks. And then the fitness function, here fitness function would be there are different ways of writing the fitness function. It could be the objective function, where you want to minimize the total distance. In this case, you can call the fitness function the cost function. In some cases, it can also be called the objective function, especially if you want to maximize. So the fitness function will be minimize total distance traveled. So basically, the fitness function will be a summation, minimize the summation. You can write it of distances between cities. You can just put it this way, okay? So you get 3 marks. You have to explain, obviously, okay? So the next question, I'm just going a little bit quick. Explain the taboo search algorithm and discuss. You can see you get only 4 marks. You get 4 marks. Don't discuss too much. Just be simple, precise and concise. And discuss how it overcomes the limitation of traditional local search methods in optimization problem. In your answer, whenever you're talking about taboo search algorithm, if you're not talking about the taboo list or the tenure, most likely the answer is not going to be right, because that's the main component of the taboo search. This is what differentiates it from the simulated annealing or any other local search algorithm. Simulated annealing has the cooling system, the annealing process. Taboo search has a tenure or the taboo list. So taboo search is some kind of a meta-heuristic algorithm. It is used basically for optimization. while it aims for good solution in large, it aims for good solution in large search spaces by combining local search with a memory-based mechanism, which is that memory-based mechanism is called the taboo list. Okay. How does it overcome? You can give loads of definition of this. How does it overcome the shortcomings of other traditional local search? Definitely, in taboo search, it tries as much as it can to avoid being stuck in local solutions. So it's going to do that through diversification. So it will diversify and intensify at some point in time. So one of the the use method is the tenure or the taboo list. This prevents the algorithm from getting stuck in local optimum or local optima, and encourages exploration of different regions of the search space. Okay. So a high tenure or a big or small tenure will, if you increase it or you decrease it, will have an impact on the diversification and intensification. Okay, so you could use that as an answer. It has also something called the aspiration criteria. Another feature would be aspiration criteria. It uses this aspiration criteria allows revisiting a solution that is currently on the taboo list if it leads to a better solution. Okay, this helps the algorithm to escape from poor choices and continue exploring potential better solutions. Okay, what is the aspiration criteria? Even though a solution is currently found in the taboo list, it can allow it. We have not seen it in the algorithm that we've seen so far, but you can also include this aspiration criteria, which is some kind of a bias. Despite it is in the taboo list, the solution is currently in the tenure, you can still revisit it. So some people would include that. So that's why I'm saying reading is very, very important to get it right. Okay. So the next question, make sure you have the question in front of you because I'll be writing answers at the same time. So make sure you have it handy in front of you to understand what I'm saying. So the next question says, you are given you're given sentences in a language that you know nothing about, where the word order has been lost. Given the words, you're requested to put them back in a sequence that has sensible meaning. For example, in English language, the word, so you have a set that has the word artificial, ease, fun, intelligence, can be put together in a valid sentence like artificial intelligence is fun. As stated, the language used is completely unknown to you. Luckily, you can use a heuristic that assigns a score to every sequence you introduce. So we're talking about heuristics here. So we're talking about informed searching method according to how ridiculous it is. So if it makes sense, the score would be high. If it's the heuristic will be high. If it doesn't make sense, like if you say intelligence fun is artificial, you can give it a lower score. Okay. So the first question: given a set of n words, what is the search space size? The search space size for this one is n factorial. Okay. There is no other answers to that. Okay. The second part, it says define a neighborhood, a particular neighborhood, a move set. Give two examples of the neighbors of the sequence artificial intelligence is fun. The neighborhood for these problems consists of possible let me just write it there, sequences that can be obtained by swapping adjacent words in the current sequence. So if you want to give an example, a neighborhood of artificial intelligence is fun. You can say artificial is intelligence fun. You can also say another example, intelligence artificial. So just minor swaps and is fun. Okay, just an example. Now the big question is part 3. Will hill climbing search always find a valid sentence? No. Right? Hill climbing, support your answer with appropriate justification in this particular case. By default, hill climbing is likely to converge to local optimum. So if it's a local optimum, it does not really mean that the sentence is fully valid. Okay, so there could be the global solution would be artificial intelligence is fun. So the likelihood that it will have a sentence that is valid is a global solution. So hill climbing, though it attempts to find global solution, it does not guarantee a global solution. Okay, so hill climbing tends to, by default, the default hill climbing is likely to be stuck or to converge quickly to local optimum. The next question is question number 4. Will a stochastic hill climbing search always find a valid solution? Again, stochastic is an improvement of the hill climbing. You can see you're given 2 marks. Don't just say no. You have to give a support. You say yes or no, you get 1 mark. But if you say the answer is yes, is no, and you're saying yes, it will be 0 marks straight away. Okay. If you say no, the problem with stochastic hill climbing is stochastic. Before we go to the problem, is stochastic hill climbing is definitely an improvement of the traditional hill climbing. Stochastic hill climbing is less prone to converge to an arbitrary local optimum, and is likely to find a better solution. This we know that. Okay. However, it is not guaranteed to find global optimum. Right. Again, we have the same problem. Therefore, or we can say theoretically, it can find a global solution as running time reaches infinity. So if the running time is infinite, it could find a global solution. That is, for this particular case, having a sentence that makes sense. Okay. However, this is not the case for brute force search. You will not be able to let it run infinite to infinity. Okay, so the answer is no. Okay, I hope this exercise was clear, helpful, and makes sense to you. Is that okay, guys? Any question? I have somebody said something in the chat. No. I hope it makes sense. Yes, for question number 1 for 12 marks, part C. We need to put all the details to get. No, you don't need to put all the details. I've already deleted it. The way I've written it, you get your full marks. And then it says 3 points for each part that is objective function. Yeah. So let me just explain question number 1. I think you Huzaifa, you have a point there. Let me just clarify question number 1. Let me just share my screen again. Please ask your question. Feel free. I'm here to help you out. So let's go back to question number 1. So question number 1. So here, design a simulated annealing, part 3, and then you see that it's asking you to objective functions. What's going to happen is that you can write. I've done it in two phases. I've written the algorithm and I've added the objective function, the initial state, the neighborhood definition. The neighborhood definition was already in the algorithm. I can just use a comment to say that I could do the whole algorithm, the one that I've written there, and wherever I'm including the neighborhood definition, I'm just going to add a comment. These are the neighborhood definition. The cooling schedule, I just put a comment in the code. This is the cooling schedule. Okay, the initial state. I just need to put the representation of that initial state, like if we're talking about the APs, for example, the initial state, I can just put it. Remember, I had the initialization. I don't remember what I've put there exactly, but I remember there was the initialization. I can put the initial state there. The objective function, if you recall, somewhere I'm calculating the fitness function. I can just put the fitness function as call a function, which is called the fitness function. And in that fitness function, I want to, in this particular case, I want to minimize the total number of APs. So it is included in there. So once you, most of the time, whenever we are going to ask you to write down design or write down the algorithm for simulated annealing, we're not going to use the word pseudocode, or we ask you to design or write the algorithm. We give you hints of what you need to include in there, so it is part of the marks. If these are not in the algorithm, or you're not explaining them afterwards, you don't get full marks. Is that okay? Is that clear now?
Yes, thank you.
Okay.
I have got the last question.
Yes, please go ahead.
Maybe a cheeky one. Do we need to learn those formulas by heart? The ones for the cooling schedule, the probability functions, and all that?
The probability, the only formula that, if you look in simulated annealing, there will be a formula. You have to know this formula. Sometimes in some questions, the formula is given to you. If you don't remember it as such, I don't remember it 100% because there are many derivations of that formula. If in case you don't remember it, you can just put it in there as a formula to, let's say, for example, for the exponential formula, you can just write exponential formula using t. You just put it there if you don't remember it. Obviously, you're not going to get full marks. Maybe if for that formula, if you're supposed to get 1 mark for that formula or 2 marks, you're going to have half of the mark, but you're not going to get 0. Okay, so if ever you forget those formulas, it depends. Some students, like, let's say, if you recall, I think I made a mistake. I think there would be exponential negative something. If I correct me if I'm wrong. Whether it's negative or not, I forgot about the formula. If I missed, let's assume there was a negative somewhere, and I missed the negative. I can see, me as an examiner, I can see that the student understanding. I can still give the full mark despite the formula is not fully correct. So these algorithms, like taboo search, does not have formula. Simulated annealing will have formula. Genetic algorithm does not have formula. Ant colony optimization have formulas. It's a little bit, we don't expect you can regroup things, like in ACO you have the alpha and the state transition probability, you have the alpha and the beta divided by the summation. It's to the power of alpha and beta, you have distance. even though you don't remember all the variables in there, you can write it as simple wording, but some key things, like just like in simulated annealing, just like in ACU, there are some variables like alpha, for example, in simulated annealing, in ACU, alpha and beta. These are core variables because these are the ones that you're going to tune. It should be in the equation. But if the equation is wrong or there is something missing, it's still acceptable because we can't expect a student to fully remember everything. But if the student is writing just a formula for probability, transition probability, then the mark can be cut in half. But if the student attempts to write the formula, but there are a few mistakes, we're still gonna give almost full mark for that formula because it is acceptable. Sometimes we give full mark, but if there are too many things, like the key variables are missing, like alpha and beta in the ACU and so on, if there is a row sign missing, these are the key things, then it's not going to be full marks. Is that okay?
Yes, thank you.
Yeah, so there are not too many formulas to remember from my side. Sometimes the formula is given to you. I think once there was a question, not for you guys, but for another batch, where just like it just came out from your slide, the pseudocode, the algorithm for simulated annealing, and part of the pseudocodes were missing. Like, for example, part of the formula is missing, the formula is there, part of the formula is missing, or maybe the cooling schedule is missing, and you have to add it in there. You can have sometimes small MCQ questions, like we have given these questions before, like it will give you a choice between 2 or 3 formulas for the decrease in temperature. Like, for example, the cooling schedule, you can have you can have an exponential decay and geometric decay, and it will ask you, or there will be other formulas for decays, and it will ask you which of the following is an exponential decay. So you just normally formulas, we tend to give you some MCQs when we want to have the exact one. Okay, so don't worry, we'll try to make your life not as difficult as it should be. But again, somebody who is using the Google Colab and practicing on the Google Colab will have no difficulty in answering any question. In the test, what we would want to know is whether, like, you will have loads of questions on experimentation, like a question, for example, you have this problem and we are using a taboo search, for example, and we figure out that the convergence graph, it is converging too quickly to the solution. What would be your take in improving the convergence graph so that it reaches close to global solution? So somebody who has played with the taboo search will know that if you try to draw the convergence graph, this is what I said, modify those codes, anything from simulated annealing, taboo search, A-star, ACO, PSO. At the end of this Google Colab, in the cells down there, just add a cell for you to be able to plot and see the convergence. So at every iteration, what is the plot? At every iteration, just plot the best solution that the algorithm is getting. And then you start to study the convergence of the graph, how it converges. If you recall, if it converges too quickly, then there is a problem. This is the best test you could do, and that's why I'm asking you to try it out. Those who do it will know what I'm talking about, and it's the best method. If it does like this, it's not a good, it's converging too quickly. If it's doing like this, it's not converging at all, and it's neither intensifying nor diversifying. Okay, it's not exploiting nor exploring. If it does like this, that's also a problem. It's diversifying a lot more than intensifying. If a normal one would be something like this at some point in time, then it stabilizes. So this is where, if you're looking at global minimum, so it should reach the global, close to the global minimum, or not necessarily the global minimum, but close to the global minimum. Okay. If you're looking at an objective function, it will be the inverse. It will be something like this. Okay, not like this. Okay, not like this. Okay, so it's just the inverse. So that's why I'm asking you, while you're tweaking the algorithm, how do you know it is performing well? It's just like a car. For those of you who are car nerds will know what I'm talking about. You want to tweak things on the car, you want to tune the car, and how do you test whether it's getting its performance? You're going to put it on a dyno, you'll have a graph, and you're going to study what's happening. So it's just the same thing. You need some kind of a convergence graph. Can be very helpful for you to understand what is happening to the algorithm. So all these algorithms that I've given you, excluding the CSP, all these algorithms from local search, BFS, DFS, local search algorithms, optimization algorithms. In the optimization algorithm, I have not given you the ACU and the PS. So you have to go and find them out, come up with these algorithms, just play around with it and come up with a convergence graph. Convergence graph is simply at every iteration, at the end of the iteration, what is the best solution? Plot the best solution. So that would be iteration 1, 2, 3, 4, 5, and it goes on like this, 100 iteration. And that's the best solution. If that is in terms of kilometers, that's 200 kilometers, that's 150, that's 100, that's 50, that's, and so on and so forth. Okay, so you try to plot it at every iteration. So plot them and then see how it performs. Okay, so when you tweak, if for instance you're looking at a simulated annealing, the cooling rate alpha, try to play with it. Remember what I said in the simulated annealing, it is very sensitive to this one and the cooling cell joule as well. So try to change it and see what's happening. If you don't use this convergence graph, you will never understand what is happening. If you look at the taboo search algorithm, there is the tenure. So as you increase the size of the tenure, something will happen. What is happening if you don't have a graph to show you what is happening, a convergence graph? You will never understand. You will never know that this is the global solution or this is a better solution compared to the previous one. So log all this, have a convergence graph. It's going to be extremely helpful. I hope that makes sense and it is helpful to all of you. Monday, we're going to have a longer session. We're going to have a session where I'm going to explain. It's going to be very mathematical, constraint satisfaction problem. You can go through the lecture notes. I've already posted questions. You can attempt them. We're going to do the tutorial within the same session itself. So we'll start at 4:30. Hopefully at 7:15 we should be done. Okay, we'll practice questions and for you to be able to understand it. Is that okay? And on Saturday next, Dr. Guru-chan will take over. It will be, you contact him for his session. So that on Monday, that will be my last session with you. Thank you very much, guys. Hope you enjoyed it. I'm sorry we couldn't make a session, a face-to-face session today, but hopefully you did understand it. Work out questions as far as you can. There is a book known as Russell Stewart. Just give me a second. Let me show you if I can share the book with you. It works, it works. If it doesn't, can't do any better. These are the best books that I've seen. I've been using Russell Stewart for almost 20 years now. There are newer versions. Oops. It's not to be working. Okay, let me just try it again. give me a second, please. I'm just trying to, if that would be great if we could get a copy of that book. Okay, for some reason it's not opening. But Russell Stewart is an amazing book. I don't know why it's not opening. I'm just gonna. I have unfortunately, I cannot share this book with you, but I have the newer version of Russell Stewart. Let me show you. Let me see if I can show you this version. This is the one I'm on about. This is a very old one. This is my first one that I'm using. This is very old, but I have a newer version of it. But unfortunately, it's not opening right now. I'm using a Windows laptop, but for some reason, it's not opening. I don't know why. But these are fantastic books. You're going to find them in the library, in the university. Russell Stewart makes one of the best. Previously, it was with Russell Stewart, and let me just try again if it opens. Why is it not opening? Russell Stewart makes one of the best books in AI. It's not that easy to understand it. It's easy whenever you start from the beginning of the book. If you miss some steps in there, some chapters, it's going to be a little bit crazy, but one of the best reference books. So try to get a copy of Russell Stewart's. There are many concepts from machine learning, deep learning, and it goes to give you the basics, okay, of AI. Especially if you want to do, it's very good in the part of AI where you want to do a constraint satisfaction problem, machine learning, optimization, searching, an introduction to neural network. It's very good. This book is very good at this. Okay. Thank you very much, guys. We'll call it a day, and we'll meet on Monday, 4:30. It's going to be a long one, and my last session with you on Monday. Okay. Thank you very much. See you on Monday. Bye-bye.
Thank you. Bye-bye.
Bye.